sir.
Yeah, hi, good evening. So, any doubts on the last class?
No, sir.
Okay, great. Okay, so let's wait couple of minutes for others to join. Then we'll start. Okay. Okay, so let's start gradually then. Yeah. Okay. So actually, one announcement. So last week during the live session, anyone from here who wanted to attend but couldn't attend, like who wanted to join this class but couldn't join this class? Because I got an email from NPTEL coordinator that few students wanted to attend this class but during the session but couldn't join. So actually I was using an extension, Chrome extension, which automatically allows the participants to join automatically. So I think that was not working. Okay, maybe that problem shouldn't happen to them. Okay, so let's start. Yeah, let me share my screen. Am I audible properly?
Yes, sir.
Yeah, thanks. Okay, so first again introducing myself, and my name is Subhadeep, and I'm a PhD student from IIT Kanpur, and I'm doing PhD in the theoretical chemistry. So today also we'll be solving 3 questions from GATE 2019 paper, question number 22, 25, 23, 25 and 52. So if you have any doubts or any confusion while solving, you can unmute yourself and ask. Okay, so let's start with question number 23. So this is question number 23 from 2019 paper, and the question is about the statistical mechanics or statistical thermodynamics. The question says consider a system of 3 identical and distinguishable. The identical is important and the distinguishable word is also important. Non-interacting particles and the 3 available non-degenerate single particle energy levels having energy 0, epsilon and 2 epsilon, and the system is in contact with a heat bath of temperature T Kelvin, and the total energy of 2 epsilon is shared by these 3 particles, and we have to find out the number of ways the particle can be distributed in these 3 energy levels having total energy of 2 epsilon. So let's first understand some of the background of StatMech. This is the basic classical StatMech. So here we have 3 particles, and they are identical. Second, they are distinguishable, and the distinguishable word is here it is very important because let's say the 3 particle means particle A, particle B and particle C. So they are distinguishable means let's say particle A and B are in energy level 0. So let's say particle A and B are energy level 0, or let's say the particle A and C are in energy level 0. So these 2 distribution are different here because the A and B particle, A, B, C, 3 particles are not distinguishable to each other, are distinguishable each other. So that means the A and B sharing energy level 0 is completely different distribution to the A and C having energy level 0. So here in this case, so we have to consider these 2 distributions separately or count these 2 distributions separately. So here the distinguishable word is important, and the third one is non-interacting. Non-interacting means the 3 particles are not interacting to each other. Okay, now the system is kept, or the system of 3 particles is kept in contact with the heat bath at temperature T Kelvin. So the heat it is in contact with heat bath means here the ensemble is, the total overall ensemble is canonical ensemble. Canonical ensemble means the number of particles in the volume of the system, total volume of the system, that means V, and the temperature of the system T is constant. So the main purpose of heat bath is keeping the temperature of the system constant. That is our desired temperature T Kelvin. Now in this setup, the 3 particles will be distributing in different energy levels according to the Boltzmann distribution or in the given temperature T. So in canonical ensemble, this is just extra information for solving this type of questions. This is not needed to solve this question exactly. So canonical ensemble means the particles, the system of particles or ensemble having number of particles in and the total volume of the system V and the temperature of the system T is constant. Now in this ensemble, the particles will be distributing in different energy levels according to the Boltzmann distribution. Boltzmann distribution. Now let's say we have different energy level like this 0, epsilon, 2 epsilon, 3 epsilon, etc. And the particles are distributing in different energy levels according to the distribution at finite temperature T. Now we can compute from this distribution the partition function. The partition function means this is I'm just giving you the extra information here. So partition function, what is partition function? So partition function means the number of ways this system of particles can be partitioned into different energy level at a finite temperature T Kelvin. So let's say there are few particles are distributed in energy level 0, there are other particles that are distributed in energy level epsilon, etc. So partition function can be computed from this expression like sum over all of the sum of all of our states like epsilon times e to the power minus epsilon over kBt, like I epsilon I, let's say epsilon I. So that means this is sum over all energy level, all possible energy level, that is 0, epsilon, 2 epsilon, 3 epsilon, etc. And what we are summing over? We are summing over e to the power minus epsilon I over kBt. Epsilon I is the energy value or the energy state of a particular, like energy value of a particular energy level. Kb is the Boltzmann constant and the T is the given temperature. Now another important thing is that the probability of having a particle in a particular energy level epsilon. Let's say you can expect this type of question like what is the probability of having a particle or finding a particle in energy level epsilon in canonical ensemble. So the answer will be just probability of having a particle at energy level epsilon. That means let's denote this with P of epsilon, which is equal to exponential minus epsilon over kBt. That means exponential minus energy of that state, which is epsilon, over kBt divided by partition function. Divided by partition function. This is the probability of finding a particle having energy epsilon. Now this total probability, that means summation of all epsilon I, P of epsilon I will be equal to 1. Okay, so these are some basics of canonical ensemble like partition function, probability of finding a particle at a particular energy level, etc. Now there are another two ensembles, which is basically another 3 ensemble, or we can construct any other ensemble from these 3 or 4 ensembles. Like another one is the microcanonical ensemble. Microcanonical ensemble means here n, v and e is constant. That means n is the total number of particles. So we are having an ensemble of system where the total number of particles is constant, and the volume means total volume of our system, so total volume is also constant, and e means energy. So energy of individual system is also constant. In the canonical ensemble, energy was not constant, but temperature was constant. Energy was fluctuating. But here in microcanonical ensemble, the energy was constant. And the third kind is the grand canonical ensemble. So third is the grand canonical ensemble. So grand canonical ensemble, that means here mu, v, T is constant. That means mu means chemical potential, which is a thermodynamic function. So chemical potential means chemical potential is constant in grand canonical ensemble. So that means the number of particles can fluctuate from system to system, but the total chemical potential will be constant. Also volume, we means the volume of overall system is constant and the temperature of the overall system is also constant here. And the fourth kind is, which is quite uncommon, which is fourth kind is the isobaric ensemble. Isobaric ensemble means pressure is constant, where N, P, T means number of particle is constant, pressure is constant and temperature is constant, which is called the isobaric ensemble. Okay, so enough detour, so let's get back to this question now. Okay, here in this question it is said that the, okay, let me just check, it is hello.
Hello, sir.
Okay, so the internet was got disconnected actually. So
Okay, sir.
so from the starting we were disconnected or in the middle of?
सर स्टार्टिंग में ही आपने लेफ्ट कर दिया था.
Okay, 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 okay. Okay. Okay, so okay, so in this question it is asked that consider a system of three identical and distinguishable non-interacting particles and the three available non-degenerate single particle energy levels having energy 0, epsilon and 2 epsilon. The system is in contact with a heat bath of temperature T Kelvin and the total energy of 2 epsilon is shared by these three particles, and we have to find out the number of ways the particles can be distributed in these three energy levels. Okay, so in this case in the okay, yeah, okay, so in this case in this question the particles are actually non-interacting. That means they are not interacting to each other, and they are they are a distinguishable particle. Sorry. Yeah. Okay, so they are distinguishable particle, and okay, they are distinguishable particle. Here this distinguishable word is very important here, because let's say the three particles are A, B, C, so they are distinguishable means we can distinguish separately these three particles. So that let's say the particle A and B are having or are distributed in an energy level of epsilon equal to 0, and also in another kind of distribution, let's say particle A and C are distributed in energy level 0. So since these three particles are distinguishable, so these two distribution are separately distinguishable. So actually we have to count these two distributions separately in this question. So here the distinguishable word is going to be very important. Okay, now the system is in contact with the heat path with temperature T Kelvin. So temperature T Kelvin. So that means the system is in canonical ensemble. That means where N, V and T is constant. N is the total number of particles, V is the total volume of the system, and temperature is the temperature of the system is constant, which is in canonical ensemble. Okay, now in the canonical ensemble, the energy can fluctuate system to system, but the temperature is constant. Now in at a given temperature T, the number of particles in our system will be distributed according to the Boltzmann distribution. Boltzmann distribution. Now let's say we have different kind of energy level like 0, epsilon, 2 epsilon, 3 epsilon, like this, etc. And the particles are distributed in different energy level according to the Boltzmann distribution. Now from these we can compute partition function. Now here I am giving some extra information to solve this type of question regarding the StatMech, basic StatMech. This is not needed to solve this question actually. So partition function is how the number of particles is distributed or partitioned in different energy level at a finite temperature T. So the partition function can be computed from this expression like sum over epsilon I exponential minus epsilon I over kBT. That means sum over, we are summing over all energy level, all possible energy level epsilon I divided by kBT. Here kB is the Boltzmann constant and the T is the temperature. Now this is the expression for the computation of partition function. And another question we can ask here, that what is the probability of finding a particle having energy level epsilon? So that means the probability of finding the particle having energy level epsilon will be exponential the energy of that state, that means epsilon I or epsilon over kBT divided by the partition function. So this is the expression for the probability of finding a particle having energy level epsilon, and the total probability, that means sum over all probabilities, will be equal to 1. Okay, so okay, am I audible now? Let me just
Yes,
check.
sir.
Yeah. Now there are another three kind of ensemble, basic 3 kind of ensemble. Now we can construct other kind of ensemble from these. The second one is the microcanonical ensemble. Microcanonical ensemble means here the N, V, E is constant. That means the total number of particles, total volume and the energy is constant. So in the canonical ensemble energy can fluctuate, but in microcanonical ensemble the energy is constant. Okay, now the third one is grand canonical ensemble. Grand canonical ensemble. Here in grand canonical ensemble, the mu v t is constant. That means here mu is the chemical potential, total chemical potential of the system, of the ensemble. That means the number of particles can fluctuate system to system, but the total chemical potential will be fixed, and also the volume will be constant, and the temperature will be constant, will be fixed. And also there are another kind of ensemble which is the isobaric ensemble. Isobaric ensemble. Now in this ensemble, N, P, T is constant, it's fixed. That means the number of particles and the pressure instead of volume and the temperature will be fixed. So these are the basic 4 kind of ensemble we'll be using basically. Okay, so now let's get back to this question. So in this question it is said that the total energy of our system is 2 epsilon. That means the energy of particle 1, energy of particle 2 and energy of particle 3 will be 2 epsilon. and we have to find out how many possible ways these three particles can be distributed with energy 2 epsilon. Okay, let's say the blue one is particle A, and the orange one is, let's say, particle B, and the green one is, let's say, particle C. Okay, so here one possible case, so there are three possible energy levels with energy 0, epsilon and 2 epsilon. Okay, now we can keep particle A and particle B with energy 0 in 0 energy level, and the particle C in 2 epsilon energy level. So in this case, so the total energy will be the 2 into 0 plus 1 into 2 epsilon equal to 2 epsilon in this case. Now this is one possible distribution. Now the second possible distribution is, we can shuffle these two particles, right, because they are distinguishable now. So that means the A and B, or A and C, or B and C, these we can separately distinguish these particles. So the distribution is separate, will be separate. If they are indistinguishable to each other, then these three distribution will be identical, because we cannot separate A, B, C. But since this question, these particles are distinguishable, so we have to consider or count these three possible distributions separately. Now the second possibility is, we can shuffle these two, that means, or shuffle these three particles, that means that, let's say, particle A is in energy level 0, particle C is energy level 0, and particle B is energy level 2 epsilon. So the total energy will be 2 times 0 plus 1 times 2 epsilon equal to 2 epsilon. And the third possible state is, again we can shuffle this, let's say particle B is in energy level 0, particle C is energy level 0, and particle A is energy level 2 epsilon. So again the total energy will be 2 epsilon. So these are three possible distribution for distinguishable particle. But if they are indistinguishable to each other, then these three distribution will be identical. So we should consider these three distribution to one distribution, not three. Now again we can keep particle number 1 in 0 energy level and 2 particle in energy level epsilon. So let's say particle B and particle C is energy level epsilon. So here in this case the total energy will be 2 epsilon also, like 1 times 0 plus 2 times epsilon, which is 2 epsilon. And again we can reshuffle these three distribution. By reshuffling this, we can get another two possible distribution, like particle number C is energy level, particle number B is energy level 0, and particle number A and C is energy level 2 epsilon. By this the total energy will also be 2 epsilon. And again by reshuffling this, we can keep particle number C is epsilon energy equal to 0, and particle number A and B is energy level 2 epsilon. So by this case the total energy will be 2 epsilon. So 4, 5, and 6. So for distinguishable particle, for three particles having energy 2 epsilon, we can get maximum of 6 possible distribution. But just a quick detour, for indistinguishable particle, if these particles were indistinguishable to each other, then we would have got just maximum 2 possible distribution, because these three distribution will be considered to one, because they are all identical or indistinguishable to each other, and these three distribution will be considered as one. So we would have got total 2 distribution, 2 possible distribution if these particles are indistinguishable. So the answer will be, the number of ways the particle can be distributed for these distinguishable, non-interacting and identical particles is 6. Okay, so for further details you can visit the lecture series on the thermodynamics classical to statistical, which is instructor is Professor Sandeep Pal from IIT Guwahati. So any doubts from this question? Okay. So okay, I guess everyone is able to join today. Okay, so everything was clear from this question. Then we can move forward to the next question.
Yes, sir.
Okay. Okay, so our next question is question number 24 from 2019 paper, and the question is it is a very short question. Question is the gas phase bond length and the dipole moment of a compound mx is 3 angstrom and 10.8 dBi respectively, and we have to find out the ionic character of this compound, that is mx, in the gas phase, and 1 dBi equal to 3.336 times 10 to the power minus 30 coulomb meter. So bond length is given, let's say compound is mx, so bond length, let's say r, bond length is given 3 angstrom, and the dipole moment 10 is given 10.8 dBi. This is experimental dipole moment, that means actual dipole moment, experimental dipole moment. Now we have to find the ionic character. Now ionic character means in a compound like this diatomic molecule mx, two atoms are m and x, and the ionic character means this compound will not be purely covalent, that means electron will not be shared equally by these two atoms. Why? Because these two atoms are diatomic with different electronegativity. If the compound were H like H2, then the electrons will be distributed equally, but here M and X have different electronegativity, that means the electron attracting power is different for atom M and atom X. So let's say the X is more electronegative than M, that means the electron attracting power of X is greater in for X atom compared to M atom. So electron will be shared mostly near the X atom here and a lesser amount of here. So the this bond is polar in nature, that means it gets ionized, it gets ionic in nature, so it's not purely covalent. So that's why we need to find out what is the ionic character of this compound in gas phase, that the percentage of ionic character in the gas phase. Okay, so to evaluate the percentage of ionic character, we have to first calculate the dipole moment. Calculate the dipole moment from the values that are given here. So that means the calculated dipole moment. Okay, let's go to the next slide. So basically the ionic character is calculated dipole moment divided by experimental dipole moment or exact dipole moment. So by computing this ratio, we can get the percentage of ionic character in a particular bond or given bond. Now the calculated dipole moment means dipole moment, we know that the charge times displacement. So here charge is electron, charge of an electron, so that means the 1.6 times 10 to the power minus 19 coulomb times displacement means this bond distance. So R, which is the given 3 angstrom, that means 3 times 10 to the power minus 10 meter. So by multiplying this, you can get the 4.8 times 10 to the power minus 29 coulomb meter. Now we know that the unit of dipole moment is expressed basically in dBi unit, right? So in the question it is given that the 1 d by the transformation function of 1 d by is 3.336 times 10 to the power minus 30 coulomb meter. So if we re-express the calculated dipole moment in the d by unit, we can get 14.3 d by. Now we have to just take the ratio, that means experimental dipole moment divided by calculated dipole moment. So experimental dipole moment is 10.8 d by and the calculated dipole moment is 14.3 d by times 100, so that is basically 75.5%. So ionic character for this bond mx in gas phase will be 75.5%. Okay, now for further details you can visit this NPTEL lecture series thermodynamics. The lectures, okay, the reference is wrong here. Okay, so here actually ionic character is calculated in the gas phase compound, because the gas phase means mx is isolated. There are no other compounds or other molecules beside this mx, so there were no intermolecular interaction between these compounds. So that's why we have to find out the ionic character of this gas phase compound. Okay, so any doubts from this question? This is actually a very short question. So basically we have to memorize or remember this expression, which is ionic character equal to just ratio of experimental dipole moment and calculated dipole moment. Now experimental dipole moment is given in this question, and we have to then calculate the dipole moment, theoretical dipole moment, which is the charge times displacement. Displacement means bond distance, which is given, and the charge means charge of an electron, which is 1.6 times 10 to the power minus 19 coulomb. Then we have to take the ratio and get the percentage. Okay, so I think it was fine. Okay, then we can move forward to our next question, which is the group theory question. Okay, so this is question number 52 from 2019 paper, and the question is basically from the group theory chapter. And here the character table of the point group D8 is given. This is the character table from the point group D8, and we have to find out the sum of these values like A, B, C, D, E, F, G, H, I, J, K. So first we have to find out this column, then we have to find out this H, I, J, K value, then we can get the sum here. Okay, so basically the D8 or Dn group is basically, here the principal axis is Cn. Here the molecule, given molecule has a principal axis Cn, and the molecule has perpendicular C2 axis. So okay, so let's say the for a given molecule the Cn axis is along the Z axis, and the molecule has perpendicular C2 axis. That means in the xy plane, that means it is principal axis Cn, and in the xy plane there will be C2 axis. That means the perpendicular to the principal axis there will be C2 axis, NC2 axis. So that's then we categorize this molecule in point group D8 or Dn, in principle, in general Dn. Okay, Dn, or there are two subcategories also, like DND and DNH. That means if molecule has principal axis Cn and the perpendicular C2 axis, and also there are diagonal plane, sigma D plane, then we categorize it, or we call it the molecule has point group DND. Now if the molecule has principal axis Cn and also the perpendicular C2 axis, in C2 axis, and then also a horizontal plane, that means sigma h is present, then we call the molecule has point group DNH. Now if the diagonal plane sigma d or the horizontal plane sigma h is not present, only the principal axis Cn and the perpendicular C2 axis is present, then we call it the molecule has a point group Dn. Now just for an Dn group, the order of the group will be just 2 times n. Now for D8 in this case, the order is 8 times 2 equal to 16. Now what is the order of the group? Order of the group is basically the order of the matrix, like basically in detailed representation, the point group can be represented by some matrices. So here in this case, for D8 group, we can describe or represent the molecule in a 16-dimensional matrices. That means 16 cross 16 matrices. So that means this is the order of the group is 16. Now quite extra things about this about the group theory. So basically these are E, C8, C4, C8 cube, then C2 prime, and the C2 double prime. These are basically symmetry operations. That means E means identity element. That means without doing anything, right? So basically we are not doing any operation or any symmetry operation on this element. So this is identity element. Or then the C8 operation, the rotation along the C8 axis, then C4 operation, C4 symmetry operation, then C8 cube, then C2 operation, C2 prime, C2 double prime. These all are basically the rotation along different axes. And the 2 is, this is basically degeneracy of a particular symmetry operation. So C8 has degeneracy 2. That means C8 has we can rotate clockwise direction and the anti-clockwise direction. In both cases, the energy or the total overall symmetry will be same. So that's why the C8 has degeneracy 2. C4 has also degeneracy 2. C8 cube has also degeneracy 2, like this. So these are basically symmetry operations and corresponding to the degeneration 2, 2, 2, like 4. And the overall sum of all these operations, all these symmetry operations, will be equal to the order of the group. Now if you sum this, 4 plus 4 equal to 8 times plus 1 9 plus 2 11 plus 2 13 plus 2 15 plus 1 16. So the overall order of the group is sum of all these symmetry operations. And this column is the irreducible representation. This term is important, irreducible representation. Now basically each irreducible representation is represented by matrices, and the dimension or order of each irreducible representation is basically the character of identity element E. Okay, let me repeat again. So the character, these 1 1 1 root 2 0, these are character. These are called character of symmetry, corresponding symmetry operation. So character of identity operation, that means E, will be equal to the dimension of irreducible representation. So basically what do we mean by the dimension of irreducible representation? Dimension means the corresponding irreducible representation can be represented by that cross that matrices. Let's say the dimension is D, so this irreducible representation will be represented by D cross D matrices, like this. Okay, so let's move forward. So here the D8 group, the order is 16. If we sum all the symmetry operations, we can get the overall order of our group, that is 16. And again we can compute the order by another method, like let's say for a particular symmetry operation, let's take this C8 symmetry operation. If you square this character times the degeneracy, like for C8 symmetry operation, degeneracy is 2. So if you take this character and square this times the degeneracy and then sum all these values, then you can also get the order of the group. That means for C8 group, let's say this is degeneracy, we are multiplying with all the characters here, so this is the degeneracy of the C8 group. Then we are taking square of each character. That means, oh god, that means first the character is 1, first irreducible representation, character is 1, then minus 1, then minus 1, then root 2, then 0, then minus root 2. So first 1 square, then 1 square, then minus 1 square, then minus 1 square, then root 2 square, then 0 square, then minus root 2 square, multiplied by the degeneracy upon symmetry operation. If you do this, you can also get the total overall order of the group, that means 16. And this is true for each symmetry operation. Square of each character times the degeneracy of a particular symmetry operation, which will be equal to just order of the group. So okay, these are basically called irreducible representation. As I told, the dimension of the identity operation, that means or dimension of identity element, will be equal to the dimension of the corresponding irreducible representation. Now let's these irreducible representation are represented by Mulliken symbol. This A1, A2, B1, B2, E1, E2, E3 are called Mulliken symbol. And how do we name this A1, A2, B1, B2? Let's first, okay, if the dimension of identity element, that means E, equal to 1, then the irreducible representation or Mulliken symbol will be can be A or B. Next operation, which is the rotation along the principal axis, that means our CN axis. Now if after rotating along the principal CN axis, the symmetry of the molecule is unchanged, that means the character is +1, then the corresponding irreducible representation will be A. And another way, if the rotation of the molecule along the principal CN axis character is -1, that means the symmetry of the molecule is changed, then the corresponding irreducible representation will be B. Now 1 and 2, how it is coming? So 1 means, now we have to go to the next operation. So from E we can get possible A and B. Now then C8, which is the rotation along the principal axis, from this we can get A or A, if it is A or if it is B. Then we have to move forward the next operation. If there are any sigma plane, then we have to count this. So if the molecule is if the next operation means this sigma 8q, these are considering. So if it is if the molecule is unchanged by any sigma v plane or any sigma plane, then if the character is 1, then we call it A1, or if the character is -1, then we call it A2, corresponding, and similarly B1 and B2. So you can see the details here, but I am not going into the detail here. So basically, if the dimension of irreducible identity element is 1, that means E equal to 1, then the possible irreducible representation will be, Mulliken symbol will be A and B. If E equal to 2, that means dimension of identity operation is 2, then the Mulliken symbol corresponding to the irreducible representation will be E. This is important. And if the dimension of irreducible representation identity operation is 3, then the corresponding Mulliken symbol corresponding to the irreducible representation will be represented by T symbol. So these three are important. If E equal to 1, then the Mulliken symbol will be A and B. If E equal to 2, then the corresponding Mulliken symbol will be E. That means doubly degenerate. If E equal to 3, the corresponding Mulliken symbol will be T. That means triply degenerate. So these things we have to consider here. Okay, now let's get back to this. Here, first irreducible representation is A1. That means A is there. So what is the value will be of E will be? Anyone? Okay. Anyone want to guess? For A1 irreducible representation, that means A is here na, so the E equal to that means character of identity element will be equal to 1. Similarly for A2 also, the character of identity element E will be equal to 1. For B1 also, the character of identity element E will be equal to 1, and B2 also, the character of identity element E will be equal to 1. Just we discussed, for A and B irreducible representation, the character of identity operation will be 1. For E representation, that means E1, E2, E3, these are doubly degenerate. That means the character corresponding to the identity operation E, this E will be equal to 2 for each case. Now if our group has T representation, then the character of identity element will be equal to 3, but there are no T representation here. So for A1 E equal be E. Okay, let's see. For A1 representation E is 1. For B1 representation E is 2. For A2 representation E is 1. For A2 representation also E is 1. For B2 representation also E is 1. For E1, E2, E3 representation E will be equal to 1. So for these values, we can get these values like A, B, C, D will be equal to 1, because the corresponding irreducible representation is A and B. Now E, F, G, this will be equal to 2, because the corresponding irreducible representation is E. So by this we can get all these values A, B, C, D, E, F, G. Okay, now we have to find out the H, I, J and K value. Now this we can find out from the great orthogonality theorem, which is a theorem in group theory, great orthogonality theorem. That means, now first we have said that the order of the group is 16. That means the group is can be represented by 16 cross 16 matrices. Now let's say it is 2 cross 2 matrix. Let's say A, B, C, D. These each row are called vector. That means each row are called two-dimensional vector. So similarly for 16 cross 16 matrices, each these type of rows will be called a 16-dimensional vector. These each row 16-dimensional vector. Now great orthogonality theorem says, for each representation, if you multiply this character, like for A1 and A2, if you multiply this character with the degeneracy, then for different representation it will be equal to 0. Now, like for a1 and a2 are different representation, different irreducible representation, so this case this multiplication will be equal to 0. That means they are these vectors are orthogonal to each other. Now how do we multiply this? First we have to take a times b times degeneracy of that operation. So here let's first start with the e operation. For e, degeneracy is 1 here, so 1 times a times b, 1 times a times b. Then go to the next operation, c8. Here degeneracy is 2. Okay, we have to multiply it by 2 here. Then 1 times 1. Then go to the c4 operation. Degeneracy is also 2. 2 times 1 times 1. 2 times 1 times 1. Then like this, if you can c2, for let's say c2, that is 1 times 1. c2 prime, degeneracy is 4, so 4 times 1 times h, here h is given. Then for c2 double prime, 4 times 1 times I will be equal to 0, because a1 and a2 are different representation. Now if you sum this, it will be equal to 8 plus 4 times h plus 4 times I will be equal to 0, so h will be equal to -1 and I will be equal to -1 from this expression. Now we have to find out the value of j. We got the value of h and I, we have to find out the value of j here. That means we can now multiply from using great orthogonality theorem, but with this and this representation, a2 and b1 representation, or a1 or b1 representation, any two you can pick, a1 or b1 or a2 b1, any two you can pick. So a1 times b1 equal to 0. Similarly for e, degeneracy is 1 times a times c. Here these two are multiplying. Again for c2, degeneracy is 2, so 2 times 1 times -1. Like this, if the total summation will be equal to 0, so the equation will be 4 plus 4 times j equal to 0, and so j will be equal to -1. Now we got the value of h, I and j. Now we have to find out the value of k here. Now for find out the value of k, we can use again the great orthogonality theorem, but with these two or these two, any two you can use. So let's say here I am using a1 times a2 equal to 0. So that means if you again do this like similarly to the a1 times a2 and a1 times b1, then you get the -2 plus k equal to 0, so k equal to 2. So first we got all these values using the irreducible representation expression, Mulliken symbol. For a1, a2, b1, b2, character of e will be equal to 1. That means a, b, c, d, all values will be equal to 1. For e representation, the character of identity element will be equal to 2. That means they are doubly degenerate. That means e, f, g will be equal to 2. Now to get the value of h, I, j, k, we use the great orthogonality theorem. That means the character, if you multiply character of different representation and sum it up, then you get the value of 0. Using this expression we got the value of h, I, j, k. Now okay, so a, b, c, d, e, f, g, h, a, b, c, d, e, f, g, e is 1, 1, 1, then 2, 2, 2, then h equal to -1, I equal to -1, and j equal to 2, sorry, k equal to, okay, j equal to -1 and k equal to 2, so j equal to -1 and k equal to 2. Now if you sum this up, then you can get 9. So the answer to this question is 9. The summation is equal to 9. And for further details you can visit the group theory lecture series. Professor is Jitendra Chugh from ISAT Pune. Okay, you can also follow the Cotton Wilkinson book, which is a very good book for to study the basic group theory. Cotton Wilkinson. Chemical application of group theory. Chemical Application of group theory. You can follow this book also. Okay, now any doubts from this question or any 3 questions? Everything was clear? Yes, no, anyone?
Yes, sir.
Okay, great. Okay, so if there are no other doubts, then okay, we'll meet in the next week, same time. So okay, so then I'm signing off today. Okay, so I'm now closing the session. Is it okay?
Okay, sir. Thank you, sir.
Yeah, thanks for joining. Bye. We'll meet in the next week. Yeah, tell your friends to join also.